thanks to the team for organizing this. I have a lot of slides, so I'm going to move relatively fast. This is mainly well, I'm going to talk about the results of this collaboration. And so we now know where the source of all of the components of the active site. They're all coming from amino acids, and very satisfying situation in that regards. And we also know about, as Dave mentioned, the maturase recipe that was discovered some years ago that helps us create this remarkable active site, very, very amazing active site to a synthetic chemist. There's a lot of synthesis being done by only 3 enzymes, but I think the some insights is that Hyd-G is really 2 enzymes. It's got 2 different machineries going on at once. And the other insight is that the maturation proceeds by building a monomer, and then it dimerizes the monomer. So with those in mind, it's a little bit more understandable. Let me just make sure I've got my timing going. So here are the jobs that need to be done, my list, for building this active site. There's and I break Hyd-G into 2 different components depending on whether we're dealing with the radical SAM or the dangler cubane, as Dave refers to it. So yeah, many steps. Most of the steps in my listing are achieved in Hyd-G. And then we have a big break that is listed with a double line where we dimerize, we assume, and then that's done within Hyd-E, and then Hyd-F finishes it up. And then there is, at least in terms of putting together the pieces, and then we have to slough off 1 CO and attach the final cubane. So this is the hypothesis that we started with, the Britt-Seuss hypothesis, we call it. Makes this fairly conventional looking coordination complex, 18 electron octahedral ferrous complex. And this is the material that is attached to the cubane, and then it dissociates, perhaps being displaced by cyanide. And the hypothesis was that this is the precursor for Hyd-E and Hyd-F. So we thought we could make this, and we know a lot about iron carbonylochemistry. So this is the kind of synthesis that we do in the bottom set of equation. We would prefer not to have something in quotes about what we're making. That is, that we would prefer to have made complex B, but we don't make complex B. We make something, and I'm going to discuss that in a minute. But the good news is that something allows Dave's group to do the biosynthesis by omitting Hyd-G. That's the core message in this part of the talk. So I'm going to talk a little bit about what is SynB and how we make it for those that might be interested in that kind of stuff. I'm more on the chemistry side of things. This is the kind of chemistry that we work with. There's an old monocyanide iron tetracarbonyl. It's an analog of iron pentacarbonyl. It's been known. It's what we use, what my coworkers use. We iodinate it to make octahedral iron, and then Scott Patnow investigated the reaction of that with cysteine, potassium cysteine. And we assume we make something as in the middle, but we definitely don't make complex B. We make something we call SynB. And that's maybe the initial compound that is formed. And it would be nice if it was that simple, but it's not quite that simple. We've tried to tame this system. We're trying to figure out why it's misbehaving. And one side thing is we've tried to attach borane. We have attached boranes to the cyanide. It slightly stabilizes things, but it doesn't really clean up the whole business. Okay, here's two structural possibilities for SYN-B. We're very grateful that the referees didn't really get on us too much about the fact that we don't know exactly what it is, mainly because I think it performs so beautifully. So option A is that it's sort of a Prussian blue type of motif where the cyanide is linked to something else. And option B is where it's attached to another iron, more or less like the dangler would be attached to the cubane. What we do know is that we can't get a proton NMR spectrum of this stuff because it's quite paramagnetic. And the paramagnetism is coming from the ferrous center that's shown as FeI2, to which these units are attached. Now, one question you always have when you're doing something like this is, how do you know you're just not making a bunch of junk? And we are quite skeptical about our own work. And the FTIR, which is shown above, matches quite nicely the FTIR that is reported by Suis and Britt for complex B. The mass spec looks decent. It's not the whole thing, but it looks decent. And of course, the real big result is that this stuff is biosynthetically quite competent. And finally, we can put this together with selenocysteine and things, and it gives us high A with selenium in it. And this is what Blackburn did the XFs on. So you can think of this as sort of the warhead that is the active part, complex B. And Dave reminds us that complex B isn't particularly happy complex anyway. And then the protecting group, which is this high spin ferrous Lewis acid. Just to put this a little bit of context so we don't think too highly of ourselves. The cysteine iron carbonyl thing goes way back. Otto Warburg group in studying heme-CO interactions. They made this compound I show there in the bottom right. And so the difference is, just to, again, for the chem nerds, is that they always get, Kramer always got 2 cysteines, and with cyanide, we can keep it so that we only get 1 cysteine. That's a trick. And once you've got 2 cysteines on, it's really difficult to pull it off. We've worked with this compound quite a bit. We can also make analogs. This is the one with cysteamine. This is decarboxylated form of cysteine. It does basically very similar chemistry. The main, in terms of spectroscopy, but the main problem is that it's not biosynthetically competent. And then here is the real tour de force coming from Grenoble. This is Yvain and his group. They have the X-ray structure of high D reconstituted or constituted with SYN-B. And so we can't reconstitute with complex B, but we can do it with SYN-B. So apparently all of the extra stuff that is attached to our SYN-B is removed, and we get this well-behaved species that, again, Roman and Yvain deduced by X-ray crystallography in the way that Grenoble is so famous for doing. Once it's inside of once the complex B, or wherever it comes from, is inside of height E, this returns back to Davis, and this is the work being done, or that was done by Lizzie Tao, remarkable postdoc working with Dave. They have figured out that the cysteine is dismembered by attack of the SAM. Here, the adenosine group attaches to the sulfur. It reduces iron 2 to iron 1. We assume, even though we don't draw it like this in the papers, we assume that the carboxylate flips off where 5-coordinate iron 1, typical geometry. We can see pyruvate coming off. We can label it and do mass spec. So we know that that looks very good. And this thing, after that, we enter sort of a world of darkness. We aren't really too sure what's happening. And one of these days, Yvain or Roman will be able to tell more of this story, but probably something with a methionine stabilized iron species. It's, again, thrown off so many ligands that it's a little bit desperate for ligands. And notice at the bottom that the comment that it's I think, a novel pathway for extruding inorganic sulfur from cysteine. It's not one of the usual mechanisms that have been, are so well known to this community. So mid-phase and late phases of the biosynthesis, this is our ideas. We think that this complex B gets really manipulated a lot and turned into this bis-SH synthon, as Dave's term, which is shown in the upper right. And then this thing is extruded from E and is then converted into the ADT derivative. We're mainly, in our group, mainly focused on doing inorganic synthesis, organometallic synthesis. So just pay homage to that work, here's the chemistry that is done. A lot of maybe you would say witchcraft, a lot of chemistry happening here. It's a terrible yield of this thing. And I just want to point out that it's a real tribute and convenient to have high yield preps, but it's a real tribute to the skill of coworkers when they've got a lousy prep and you still pull out the compound. Since then, we think we're on the road of getting this yield way back up because we've revised this all quite a bit. And this is how we think this all happens. This is not biomimetic, but this is for again, organometallic chemistry. This is probably how this dimer forms. There's a structure of the thing that we call the Fe2SH2 synthon. It's got these gigantic flying saucers attached to it. Those are the solubilizing reagents that Yu Zhang uses. They're crown ethers and they're attached to cyanide. Cyanide is always sticky. And there you can see the SH groups. And the H's are resolved by X-ray crystallography. We know where they are. Somewhat novel. Here is some of the NMR characterization. Again, I'm speeding right along. I'm not sure everybody's keeping up, but there's the NMR characterization. The thing about our groups on sulfur, bridging sulfur, is that they have various regiochemistry or stereochemistries, and we can really tear this thing apart. We know we have a lot of experience with this kind of entity. The crystal structure is a slightly unusual geometry or isomer, and we can figure out a lot from the carbon and NMR, both with cyanide and CO. I'm not going to drag you all through all that stuff. We can label these things a lot. Iron labeling is a little bit awkward, but the cyanide labeling is straightforward. So that was the old days when we first started in. We could use SynB to skip G, and now we can use this new synthon and skip E. And as Dave mentioned, Joan Broderick has some things to say about nuances and some aspects about how that actually comes about. So that's the team. We're completely indebted to them. how's my time? Do I have a minute?
I must admit, I've also completely lost track of time. It's, yeah, I guess it's
yeah, I'm just going to mention a couple more things. So yeah, one of the big questions is sort of within Hyd-E, how is this thing being assembled? And Elaine has been sort of promoting the idea that maybe the monomer is stabilized by a thioether, and then it's waiting in a chamber below the action chamber, below the SAM chamber. And that monomer, I used to have a French postdoc, she always said monomere. So that monomere is waiting for the second one to be created. And then when the second one is created, then presumably the first monomer, the SH, binds to the second one, and there you have the bis-SH synthon. And then one more sort of surprise is for the hardcore biochemists, we all know about lipoic acid, and we're all on our minds, at least Dave's and my mind and Joan's mind, about the SS versus bis-SH. Something similar could definitely be happening in this chemistry, and we know referee has brought it up for us, but we've been quite, at least I've been quite mindful of it. And so the synthon business isn't quite finished yet. We still have some work to be done in addition to some labeling. And lastly, so we have, well, I think I've gone over this. I wanted to end there. So thank you very much.